I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the previous year questions from the section analysis that have appeared in the CSIR National Eligibility Test. In this video, we discuss 3 questions, question number 12 to 14. All these questions are suitable for all these examinations. Right. This question has appeared in 2014 December examination. And the question is related to the number of surjective maps. The given question is the number of surjective maps from a set of 4 elements to a set of 3 elements is. We are given 4 options. Let's now discuss the solution of the problem in detail. We recall a result. Let A and B be finite sets with m and n elements respectively. Then the number of onto functions, that is the number of surjective functions f from A to B, is given by this formula. Sigma k is equal to 0 to n minus 1 to the power of k into n c k multiplied by n minus k to the power of m, where m greater than or equal to n. If m less than n, then the number of onto functions is 0. There are no onto functions in this case. That is the case when m less than n. Right. We will answer the question. The number of surjective maps from a set m is equal to 4 elements to a set n is equal to 3. Observe that m is 4, n is 3, m greater than or equal to 4. Right. We apply this formula. Sigma k is equal to 0 to n minus 1 to the power of k into n c k into n minus k to the power of m. That's equal to sigma k is equal to 0 to n is 3 into minus 1 to the power of k into n c k, that is 3 c k into 3 minus k whole to the power of 4. Now, for k is equal to 0, you will get 3c naught into 3 minus 0 to the power of 4 minus 3c1 into 3 minus 1 to the power of 4. Minus is because minus 1 to the power of 1 is minus 1. When k is equal to 2, minus 1 to the power of 2, that is plus 1 into 3c2 into 3 minus 2 to the power of 4. When k is equal to 3, it is 3 minus 3 is 0. Don't write. I'm sorry. Now, 3c naught is 1 into 3 power 4 minus 3 into 2 to the power of 4 plus 3 into 1 to the power of 4. I'm sorry, a problem with my cough. Now, this is equal to 81 minus 48 plus 3. That is equal to 84 minus 48. That is given to be 36. And the answer appears against option 1. Therefore, option 1 is true. And the answer to this question is option 1. Right. Right. Instead of this formula, what we have written here, you can use this formula also. Sigma k is equal to 1 to n minus 1 to the power of n minus k into k to the power of m into nck. Right. This formula, the earlier formula, both are same only but written in a different form. Right. Suppose now we ask a question, that is the number of surjective maps from a set of 3 elements to a set of 4 elements. The same question, we reverse the number of elements. 4 elements to a set of 3 elements. Now we have written 3 elements to a set of 4 elements is, and we have given a blank, fill the blank. Write your answer in comments box. In the comments, please write your answer. Now, that is the detailed discussion of the solution of this problem. Let's move to the next question. Right. This question has appeared in 2016 June. It is related to the discontinuities of a monotone function. The given question is, let f from R to R be a monotone function. Then we are given 4 options. Option 1, f has no discontinuities. Option 1, f has no discontinuities. Option 2, f has only finitely many discontinuities. Option 3, f can have at most countably many discontinuities. Option 4, f can have uncountably many discontinuities. The question is basically, for a monotone function, how many discontinuities are there? Right. Let's now discuss the solution of the problem in detail. We have f from R to R, a monotone function. We mean by a monotone function, it is either an increasing function or a decreasing function. Let us recall a result from analysis. Let f from R to R be a monotone function on R. Then the set of points of discontinuity of f is a countable set. Note, for a monotone function, the singularities are limited to countably many jump discontinuities or removable discontinuities. Now the discontinuities are limited to a countably many, and what type of discontinuities these are? Jump or removable discontinuities. And these jump and removable discontinuities are called discontinuities of first kind. Right. Now, let's answer the question. Let us take option 3. F can have at most countably many discontinuities. Therefore, the option 3 is true. Option 1 is not true. It says no discontinuities. But whereas here a monotone function has countably the number of discontinuities are countable. And option 4 is not true. It says uncountably many. Right. Now, what is the guarantee that f has no finitely many discontinuities? So, you consider the greatest integer function, or sometimes called floor function, or sometimes called box function, denoted by f of x is equal to floor of x or bracket x, is a classic example of a monotone function that has infinitely many jump discontinuities. Therefore, here is an example which accepts infinitely many jump discontinuities. Therefore, the option 2, that f has only finitely many discontinuities, is not necessarily true. Therefore, option 2 is not true. The answer to this question is option 3. That is the detailed discussion of the solution of the given question. Right. We move on to the last question, question number 14. And this question has appeared in 2018 June, and it is from the section linear algebra, and it is related to non-negative value of a quadratic form. The given question is, given that there are real constants a, b, c, d such that the identity lambda x square plus 2xy plus y square is equal to ax plus by whole square plus cx plus dy whole square. This holds for all xy belongs to R. This implies we are given 4 options related to lambda. Option 1, lambda is equal to minus 5. Option 2, lambda greater than or equal to 1. Option 3, 0 less than lambda less than 1. Option 4, there is no such lambda belongs to R. Let's now discuss the solution of the problem in detail. We are given a, b, c, d. They are real numbers, real constants. Given lambda x square plus 2xy plus y square is equal to ax plus by whole square plus cx plus dy whole square for all xy belongs to R. Note down, ax plus by whole square plus cx plus dy whole square is greater than or equal to 0 for all xy belongs to R. Because it is the sums of the squares, which is always non-negative. This will imply lambda x square plus 2xy plus y square is greater than or equal to 0. This will imply the quadratic form denoted by q of x comma y is equal to x transpose ax greater than or equal to 0 for all capital X is the column vector xy belongs to R, where the matrix of the quadratic form is A is lambda 1 1 1. It is a 2 by 2 matrix. So the lambda x square plus 2xy plus y square is a quadratic form. It is greater than or equal to 0. It says that this quadratic form is semi-positive definite. If it is strictly greater than 0, we call it as a positive definite quadratic form. But here it is given greater than or equal to 0. Therefore, it is a semi-positive definite quadratic form. Right. When it is a semi-positive definite quadratic form, all the principal minors are non-negative. The first one minor, principal one minor is lambda greater than or equal to 0, and the two minor, principal two minor is the whole determinant lambda 1 1 1 greater than or equal to 0. The greater than or equal to 0, 0 is missing here. 0 is missing here. This will imply lambda greater than or equal to 0. The determinant is lambda minus 1, which is greater than or equal to 0. In the above, greater than or equal to 0 is missing. So lambda greater than or equal to 0 and lambda greater than or equal to 1, the common you take, that is lambda greater than or equal to 1. So the answer is appearing against option 2. Therefore, the answer to this question is option 2. And the answer to this question is option 2. That is the detailed discussion of the solution of the given problem. And all the 3 questions are easy questions. I am sure that you have understood the solutions of these 3 questions. Thank you for watching the video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Let's hope to meet you once again in another episode of learning. enjoy learning mathematics. I wish you all the best. Thank you.